Welcome. So the problem at hand is to show that if a function f of z given by u plus iv is an analytic function, then u and v are both harmonic functions. Now, by the fact that f of z is harmonic, is analytic, then it implies that u and v satisfy the Cauchy-Riemann equations. So solution or proof. So let f of z equals to I plus iv be analytic then partial u partial x equals to partial v partial y and partial v partial y partial v partial x is negative or partial u partial y is negative of partial v partial x. So call this one question 1, call this one question 2. So these are what we call the Cauchy-Riemann equations, i.e. f of z equals to u plus iv is analytic implies u and v satisfies the Cauchy-Riemann equations. So that's what we mean by f of z u plus iv being analytic. Now what we are going to do, we are going to differentiate each of these two equations. So equation 1 with respect to x and equation 2 with respect to y. So differentiating 1 with respect to x, we get, now this side will give us partial squared u partial x squared. This will give us partial squared v partial x partial y. Call this one equation 3. And then again, differentiating the second equation 2 with respect to y. We get, so here left hand side will give us partial squared u partial y squared equals to negative partial squared v. Now partial y partial x. So call this one equation 4. So adding 3 to 4, we have partial squared u partial x squared plus partial squared u partial y squared is equals to, so partial squared v partial x partial y. That's what we have on the right hand side. And then plus minus partial squared v partial y partial x. You see this is the same as partial squared u partial x squared plus partial squared u partial y squared equals to partial squared v partial x partial y minus partial squared v partial y partial x, and this is equals to 0 since partial squared v partial x partial y is equals to partial squared v partial y partial x. So since u satisfies the Laplace equation partial squared u partial x squared plus partial squared u partial y squared equals to 0, then u is harmonic function. So that's case 1. Now let's see for v. Now, again, now differentiate question 1 with respect to y. So remember, this is question 1. So let me just rewrite them. Remember, here we have partial u partial x equals to partial v partial y. So this is what we are calling question 1, and partial u partial y is negative partial v partial x. So I'm saying that we differentiate this with respect to y. So we get partial squared u partial y partial x equals to partial squared v partial y squared. Let's call this one equation 5. And then differentiate equation 2 with respect to x. We get our differentiating. So we can say differentiating. So this one will give us partial squared u partial x partial y is negative partial squared v partial x squared. Let's call this one equation 6. Now say equation 5 minus equation 6 gives, so I'll get, so this one is the same as partial squared v partial y squared. Now minus minus will be plus partial squared v partial x squared equals to partial squared u partial y partial x minus partial squared u partial x partial y, i.e. partial squared v partial x squared plus partial squared v partial y squared is the same as 0 since partial squared u partial y partial x is equals to partial squared u partial x partial y. So this means V satisfies the Laplace equation, which implies that V is a harmonic function. So we have successfully shown that U and V are harmonic functions because they satisfy the Laplace equation. And such functions, just in summary, such functions, U and V, are called conjugate harmonic function if U plus IV is also analytic function. The ideas, or simply we mean conjugate harmonic functions are functions which are harmonic and at the same time satisfy the Cauchy-Riemann's equations. So that's how we're supposed to prove that given result in the problem. Thank you.